afternoon session. Our first speaker. Should I use this thing? Welcome to the afternoon session. Our first speaker will be Vera Fischer from the University of Vienna, who will speak on spectra and definability.
Thank you, Ralph. I want to thank the organizers for this wonderful meeting. It's my first time in Gdansk, and I really enjoyed it. It's a very beautiful place, so thank you. All right, so I will talk about some aspects of set theory of the reals. So now we are going to combinatorial sets of reals and the so-called classical cardinal characteristics of the real line. And we'll see some recent developments in the study of this subject. And in particular, I would like to go through three lines which brought us to some very interesting, for me, combinatorial objects. All right, so it's a logic conference, so I'll remind you some definitions. All right, so typical examples, mad families. Everyone knows what's maximal homogeneous disjoint families. But we'll be also looking at some relatives of these maximal homogeneous disjoint families, which are not that well known. Families of functions, eventually different functions. Cofinitary groups, eventually different functions, families, which also have a group structure. But also, we will go into some other combinatorial objects like independent families or ideal independent families. So there are two aspects that would be of particular interest for us. On one side, we'll be looking at what are the possible cardinalities of the sets. And we'll see that, in fact, providing a generic extension in which there is a combinatorial object of desired set of desired size is sometimes a very non-trivial task. And then we'll see to what extent the projective complexity of these combinatorial sets of reals distinguishes them. All right, so the easiest of all these objects is family of functions. And we'll be interested in functions which have the property, families of functions, that from some point on, their graphs do not intersect. Now, such functions are said to be eventually different, which is suggestive. And clearly, if we have a family of eventually different functions, then the graphs of these functions are just an homogeneous disjoint family. So this is a relative of homogeneous disjointness. And what we are interested in, typically, we are looking at the minimal cardinality of a maximal such combinatorial set of reals. So a maximal eventually different family. Maximal under inclusion. Now, of particular interest is this minimal cardinality, but we'll start asking the question, well, apart from the minimal cardinality, what other possible sizes can such combinatorial sets of real have? All right, now this is AE. E stands for eventually different, the minimal cardinality of a maximal eventually different family. All right. Now, what will happen if you impose a structure on such a family? With other words, we want a family of eventually different functions, which is closed under composition. And now, if you think about the definition for a moment, you'll see that equivalently, it is equivalent to require that every non-identity element of our family has only finitely many fixed points. So such groups are said to be cofinitary. And we'll be interested in maximal cofinitary groups, maximal under inclusion. So the minimal cardinality of such an object is denoted AG. G stands for group. Okay, so if we have a maximal cofinitary group, is it necessarily a maximal eventually different family? Can we separate these notions? And these are very difficult open questions. All right, so we'll see what, nevertheless, what can be said about these objects. I will keep on giving open questions throughout the talk. All right. So one very important distinction is what is the relation of the homogeneous disjointness number and its relatives, these very close relatives, minimal cardinality of a maximal eventually different family or minimal cardinality of cofinitary group to the uniformity of the meager ideal. All right, meager sets, we all work with them. So on one side, the homogeneous disjointness number is independent from the uniformity of the meager ideal. All right. On the other hand, though, surprisingly, we have a ZFC relation between the uniformity of the Meager ideal and these close relatives of almost disjointness. So they, after all, they're relatives, but they seem to be quite different. Another distinction comes from their projective complexity properties. So on one side, we have the celebrated result of Adrian Matthias, that there are no analytic maximum almost disjoint families. On the other hand, they are Borel maximum eventually different family and Borel confined interior groups. So these objects turn out to be quite different after all. All right, so one way to think, I know that in the audience we like represent very different areas of set theory. So one way to think about these characteristics is what information they give us about other sets of reals. For one way to think about uniformity of the meagerness is that if every set of cardinality alpha is meager, this means that the uniformity of meagerness is strictly bigger than alpha, then there are no maximal eventually different families of cardinality alpha. This is one way to think about uniformity of meagerness, let's recall AE. So this information that cardinal characteristic embed is useful, is practical. It gives us more information about the reals. All right. So now, for a very long time, the subject has been entirely focused on the minimal cardinality of such combinatorial set of reals. However, with the development of our understanding of the relationship between these objects, and also to a great extent also forcing techniques, the focus shifts. We start asking, to what extent can we actually control, to what extent can we understand the sets of possible cardinalities of these combinatorial sets of reals, and also not only their cardinalities, their projective complexity. Does it matter what size they have with respect to their complexity? Surely, but can we control this? Can we obtain generic extensions in which we can demand this? So these are the two aspects in which we are going to move and see some interesting combinatorial objects that will come out of these studies. All right, so well, if we are to add a size, a combinatorial object of a desired size, so a typical, a standard method that anyone who knows forcing would think of is, well, let's add one generic real which extends our combinatorial set of reals at a time. So typical example, almost disjoint coding. We start an almost disjoint family, we add a real almost disjoint from all the reals in the ground model. From the given family, we enlarge the almost disjoint family to a larger one. All right, this sounds good. And but it's not always that easy how to do this. So for confined interior groups, if you think, I went through the definition, if I just want to add a new generator to a confined interior group via forcing, I have to worry about a number of additional properties, not only about the number of fixed points of this new generator. I have to guarantee that any possible new permutation that would come together with the new generator has only finitely many fixed points. And in fact, that's a celebrated result of Zhang, which is already quite old, which will show that indeed there is a forcing notion which adds a new generator to a given confined interior group. All right, so what does this tell us about the possible cardinalities of these objects? Well, if we just do finite support iteration, these forcing notions are CCC, we can increase the size. Are we going to get maximality? And what is necessary to get maximality? So if I just start adding con reals, I can produce as large as I want independent family, but it's not going to be maximal. So there is something more to such arguments, which allow us to add a combinatorial set of reals of desired size with just adding one real at a time, a property to which we refer as diagonalization. So these generic reals has also some relation to the ground model reals which are not in the family and somehow eliminates undesired objects. So I'll come back to this point later. But that's a very important feature which would appear again and again. So what stands beyond this technique? Well, we are actually relying on this diagonalization property to claim maximality. So any set of reals, if we have an iteration of uncountable cofinality length, will be added at some initial stage of the construction. And so the generic, we leave it to the generic to guarantee that the family is maximal. It would eliminate these intruders, these undesired sets from the ground model somehow. But what is left is Aleph omega. With this procedure, we cannot capture our tail, and if the cofinality of the iteration is omega, because there are reals that do not really appear at any initial stage of the construction. All right, so how does the problem, what does this mean for these combinatorial sets of reals? So on one side, for mad families, the situation, this is probably the set of reals that we know best. We have Heckler's forcing for adding a maximum almost disjoint family with finite condition of arbitrary size. So this forcing notion has very nice combinatorial properties. So essentially with any index subset, we can associate a suborder which completely embeds into the larger forcing notion. And this is the reason that in fact this forcing notion can be embedded into the template construction of showing that consistently D is less than A, and eventually leads to the consistency of A being Aleph omega. So we can force, not only guarantee that there is a mat, okay, Heckler's poset, we can add any size maximum almost disjoint family, but guaranteeing that there is no smaller one requires more. All right, so for cofinitary groups, one can generate, there is such strong forcing notion which has these very good combinatorial properties, and in fact one can not only add a maximal cofinitary group of desired size, but also this forcing notion has these good properties, and one can guarantee that consistently the minimal size of a cofinitary group is Aleph omega. And that's all very good until we start hitting really difficult problems. Now going back to the conreals and independent families, what about having the independence number Aleph omega? So remember that if we add conreals, the conreals are independent, but they don't have this diagonalization property. So essentially, and it's only very recently, we were able to show that consistently there is a maximal independent family of size Aleph omega, but that's it. We still do not know how to show that consistently the independence number, the minimal size of such a family, is Aleph omega. And had we had such a way to add an independent family with such very nice combinatorial properties, yes, we would have been able to answer this question. But for the moment, we do not know. All right. So going back to the other aspect of the studies, definability. So how I mentioned there is a Borel maximal cofinitary group, but that's a result which was actually gradually obtained. So first, Sugao and Tijang showed that in the constructible universe, there is a cofinitary group with a coanalytic generating set. All right, then Casterman showed that there is in fact, the whole group can be coanalytic. And much later, Horowitz and Schiller constructed a Borel maximal cofinitary group. All right. Aha. But we are committing here these examples. The Borel maximal cofinitary group is always of size continuum. The examples in L, they're also in size continuum, but we have CH. So a very natural question is, well, if we are looking also at the spectrum and possible sizes, what can we say about the projective complexity of such combinatorial sets of reals in models of large continuum? All right. All right, and so we have another task. We set ourselves another task. We want to have a nice combinatorial object, cofinitary groups, which is indestructible and also has a nice definition. All right, so the first thing we could do is, in fact, we just show that there is a coanalytic, co-indestructible maximal cofinitary group. All right, and so the existence of a pi-1 maximal cofinitary group is consistent with the continuum being arbitrarily large. So how do we construct this object? Well, we construct it in an iteration of length omega 1. It's a recursive construction. But in fact, Well, we're not cheating, but we really, at every countable stage, we are meeting a collection of dense sets. The dense sets representing requirements. The only thing is that since we only have countably many dense sets, we do not really do forcing, but it is fair to say that the proof and this construction is indeed forcing inspired. And all right, so how are we to do this construction? So I want to give you just some idea of how these different requirements on what we want to obtain with respect to the cardinal characteristics, to what kind of different combinatorics it brings us. So the way that this co-indestructible co-analytic construction maximum cofinitary group is obtained is we work with finite approximations to the members of the group, and we require from these finite approximations to encode reals, because we want to have a nice definition. And so how do we encode reals? Well, if this, we will work with finite functions which are intended to be approximations to the members of the group, and they encode reals in a natural way, just from the powers of these finite approximations at a given parameter. They coincide, they have dirity of this real that you want to associate. All right, so this is the general idea. And then eventually, of course, we want to have a whole real. So the partial order that essentially stands behind the construction consists of, now this should remind you a little bit of almost disjoint coding, consists of finite approximation to a new generator, the new member of the group. Now we have finitely many promises. These are possible members of the group which occur after we add this new generator. So we have to worry about the fixed points of these new members of the group. And we have a set of parameters for each permutation associated to a member of this finite set. We have a parameter with which we are going to be encoding a certain real. So everything is finite. And this is the basic object that would help us to construct this nicely definable cofinitary group. All right, I do not want to go too much into the details of how this forcing works. What is important is that once we have all our finite approximations, we do get a new generator. So we have a generic group, the generic filter, we have the new permutation. And here is what are the properties. On one side, we do extend the ground model group, or just the initial segment that we have constructed. And here is the second diagonalization property that I mentioned already. If we have a permutation which is not in the group we have constructed so far, then the generic real essentially meets it infinitely often. Or broadly said, this generic this intruder, we speak about elimination of intruders. It's a discussion if they're intruders or imposters. I call them intruders. Saharon calls them imposters. Anyway, so these objects, if they threaten to violate maximality of this object that we are recursively constructing, we are guaranteeing that the generic is preventing the situation by hitting it infinitely often. And we have this encoding requirement. All right, so that's great. What do we obtain? We obtain a co-indestructible pi11 maximal cofinitary group. And so we have the evaluation of the cardinal characteristics in the Cohen model. The bounding number is small, the dominating number is large. All right, so that was a lot of effort to obtain one constellation with a pi11 witness. What if we want another constellation? What do we do? This method does not help. So we had to start again. And in fact, we had to develop a whole new machinery to anticipate possible Sachs names for reals. And moreover, in our first attempt, we could only produce a pi11 maximal eventually different family of reals. And only recently, so this result is a couple of years old, we could also construct a co-analytic maximal cofinitary group. All right, so So the idea is very different. We do not work with finite approximations, but we work with the property which we refer to as a not eventually different, NED property, which essentially says that a forcing notion has this property if whenever we have a countable family of functions and a name for a real which is forced to be eventually different from every member of the family, then we can find a ground model function and a condition which forces that this name and the ground model function are infinitely often equal. So very different. It has nothing to do with finite approximations. And this property turns out to be the key feature which allows us to obtain first maximal eventually different family and later also a cofinite coanalytic maximal cofinitary group. All right. So what happened with this encoding of reals? Well, for maximal eventually different families, it turns out that to obtain a pi11 maximal eventually different family, it is sufficient to obtain a sigma 1, 2. And this situation is not unique for maximal eventually different families. The same holds for towers, maximal almost disjoint family that was first observed by Tasgaard-Törnquist. Then we could show that if there is a sigma 1 to define more maximal independent family, there is also pi11. The same holds for towers, but for groups, this is still open. So somehow the presence of this group structure makes the object more difficult to understand and work with. All right, so thanks to the NED property, now we have yet another constellation that the dominating number can be small and we can have a coanalytic witness for a maximal eventually different family. All right, well, for everyone who knows the combinatorial cardinal characteristics, there is so much more. That was all great, a lot of effort, but there is so much more that we might want to do. We finally got some idea how to do this. So we essentially construct an object which we can think of as being, well, for our purposes, very robust, indestructible. Indestructible for various forcing notions, and it is in a certain sense inspired by tight, almost disjoint families. All right, so initially it wasn't clear how to generalize this tightness, but we did come up with I think quite a good notion. So we start thinking of family of functions as just we think of them as points in the plane, and so we can think of a tree, a finitely splitting tree, being covered by a family of functions. And moreover, we say that a family of functions almost covers a tree T, if just when we look at this set of pairs in the plane, it is almost contained into the points covered by the family of functions. All right, and so in analogy with the ideal associated to an almost disjoint family, we speak about the tree ideal generated by a family of functions. Now, this is really not an ideal, it is just a name, which consists of all trees T, which have the property that for some finite subset of the given family of reals, the cone above this tree is covered by the graphs of these functions. All right, and we say that the tree T is positive with respect to a family of functions if for each node in the tree, the cone above this node is not almost covered by a finite element of the tree. So finite family of functions. So this is really the analogy with being positive with respect to an ideal generated by a MAD family or AD family. All right, so what is a tight family? Well, we have the following definition. If we have a tree and a real, then we say that this real densely diagonalizes the tree if for every node of the tree there is a branch through T, which is infinitely often equal to this real. And tightness is just saying that an eventually different family is tight if whenever we have a countable family of trees, which are positive with respect to this family of functions, there is a single real in the family which densely diagonalizes all these trees. All right, so a little bit technical. Aha, what happens? Well, tight eventually different families are maximal. They exist under CH, they exist under MA sigma, sigma linked. Aha, and now we stumbled into something more interesting. They're never analytic. And so in particular, the maximal eventually different family, the Borel maximal eventually different family of Horowitz-Shela is different than this object. All right, so I just want to see, okay. Aha. So why are those, so why do we think of these tight families as being helpful? Well, they're co-indestructible. There is a co-analytic tight eventually different family. And so once again, we get one of the constellations with the pi1-1 witness. But much more is true. In fact, for a various, one can develop a notion of strong preservation of tight eventually different family, which pretty much works as preservation of properness, which allows us, so this is really in the style of preservation of properness, countable support iteration of proper is proper, which brings us to the following interesting result. Tight eventually different families are indestructible by a long list of partial orders. Sachs, Miller rational perfect set forcing, Miller forcing, infinitely often equal forcing, Shela's poset for diagonalizing a maximal ideal. And so we in fact obtain a whole bunch of other interesting constellations with co-analytic witnesses to each of those relatives of almost disjointness. And this is all thanks to this notion of tightness. So we found in a certain sense a uniform method presentation. We found combinatorial properties which can anticipate all of these forcing notions. All right. That's so great. What is interesting, and that of course we first obtained those of size continuum, but what turns out is that if we are to adjoin an almost disjoint, a maximal eventually different family by just studying generically real after a real, this recursive construction I went at the beginning with, we will end up accidentally, or possibly not that accidentally, with exactly such tight maximal eventually different family, tight eventually different family. And that's interesting, as you're going to see, as the similar phenomenon happens also for other combinatorial sets of reals. Now, keeping the overall picture in mind, well, what about members in the spectrum of, say, cofinitary groups, which are strictly between Aleph1 and the continuum? Can we say anything about the projective complexity of such cofinitary groups? We put so much effort into controlling the least projective complexity of a witness for Aleph1 in the spectrum, or so much effort into providing this Borel maximal cofinitary group. What about everybody else? Well, so we introduce the notion of a good projective witness, and whenever we have such an intermediate size in the spectrum, we'll say that a group is a good witness if it is of cardinality mu and has lowest projective complexity. So this is written for cofinitary groups, but of course one can think about all kind of other combinatorial sets of reals in this context. All right. So what can we say about these properties? Well, if you think a little bit about them, every sigma 1 2 cofinitary groups is either of size Aleph1 or continuum. And so the lowest possible projective complexity for a witness to intermediate size cardinality is pi1 2. And now our techniques of constructing a group with finite approximations come again into play, and this in fact plays a major role into the following result, that we can in fact have a pi1 2 witness for an intermediate size of the spectrum. Okay, but the game should start slowly becoming, that's an interesting, very interesting forcing construction. Now, on one side, I want to control the spectrum, and on the other side, I want to control the projective complexity of various witnesses in the spectrum. So how far can we play this game? So that's where we are currently. It turns out that, say, for maximal eventually different families, we can speak about optimal projective spectra. We have a generic extension. This is the cone extension, in which the spectrum is actually very simple. It consists only of two cardinals, Aleph1 and the continuum, any eventually different, maximal eventually different group, which is of any other size, is not maximal. So the spectrum is maybe a little bit boring. We can have optimal witness for Aleph1 and for the continuum. These are two very, very serious results. On one side was our indestructible co-analytic, eventually different family. On the other hand, we have Horowitz-Shelah. All right, so using these finite approximations, we can contain completely different construction. We can have an optimal witness for any intermediate size, pi1, 2. We can have still the Borel witness for size continuum. And the best we can do is we can get a pi1, 2 witness for Aleph1, but this is not optimal. So we still don't know how to do it. So that's where we are. Essentially, we can anticipate only 2 out of 3 demands. And the situation with cofinitary groups is very similar. And essentially, the situation with any other combinatorial objects that we have for now is just the same. All right. So now I want to say a few words about independent families. So independent families, remember, are families of infinite subsets of omega with the property that whenever we have two finite subsets, then this set, to which we refer as a Boolean combination, is infinite. All right, we are interested in maximal independent families. Maximal under inclusion, and again, we will be talking about the minimal cardinality of a maximal independent family and the spectrum of such families. Now, what is interesting is that our understanding of even how to produce maximal independent families of desired size, well, at least up to a few years ago, was much less developed than our understanding about maximal almost disjoint families. All right, so a very convenient way to think about these Boolean combinations is just to think of functions with finite domain from the family into 0, 1. And what is a Boolean combination? Well, this is just the intersection of the preimage of 0, all the sets which are sent to 0, with intersected with the complement of the sets sent into 1. All right, and if we have a function with larger domain, this means that we intersect more sets when we evaluate the Boolean combination associated to this larger function, function with larger domain. So we speak about strengthening of a Boolean combination. So this is a smaller set. So, okay, so maximality. It turns out that there is a stronger notion of maximality, which would be combinatorially robust and will survive various extensions. But this was interesting how this was obtained. And so let me tell you a little bit more about this. So on one side, we have dense maximality. What is dense maximality? Maximality just says that if I have a family outside of this independent family, then there is a Boolean combination which will not like this family. This means this new set, which means that this set does not split the Boolean combination. Okay. Dense maximality says that for every set and every Boolean combination, I can find a strengthening of this Boolean combination, which does not like the set. Okay, dense maximality appeared a long time ago in the work of Goldstern and Shelah on the consistency of R less than U. All right. So dense maximality is good, but is still not what we want. So if we have an independent family, then the family of all subsets of omega, which have the property that every Boolean combination can be strengthened to a Boolean combination contained into the set, is clearly a filter. And this filter captures very important properties of independent families. It has a name. We speak about the density filter. So a densely maximal independent family is said to be selective if in case this density filter is Ramsey. And so, as you're going to see, such selective independent families are actually very robust with respect to forcing. So, in a certain sense, they're maximal in a very strong sense. All right, so they were first constructed by Saharon Shelach in, I think, 1984. They exist under CH. Good news, now we can have them of arbitrary size. And they are indestructible by countable support iterations and products of Sachs forcing. That's an unpublished result of Todd Eisworth. And it essentially, one can read it off from the proof of the consistency of I less than U. All right, so we have, again, the independence number can be small, can be smaller than the ultrafilter number, but there are so many other possible constellations. What can we say about those? Well, I'll come back to this point, but before that, let me comment on the projective complexity of such families. They're not analytic. On the other hand, we can have a model in which there is a co-analytic witness to I less than Aleph1. In fact, if we start over the constructible universe and we just take a Sachs extension, that's what will happen. However, these results were only gradually obtained, and it took some work. So about the optimal projective spectra for independence families, as you can see, we are far, far behind compared to MAD families or cofinitary groups. In the Sachs model, there is no maximum independent family of any other size than Aleph1 on the continuum. So the spectrum is, in a certain sense, minimal. There are only two cardinals in the spectrum. We can provide an optimal witness for the smallest size, and we still cannot provide an optimal witness for cardinality continuum. So there is a lot that one can obtain and wish for. Now, what it turns out, it is not that clear how to add a maximal independent family of arbitrary size, of cardinality different than the continuum and Aleph1. So we do not want preservation properties. We want to be able to have some kind of diagonalization, and this is possible. One can have this feature that in very broad terms, I said we add a new generic which extends a given combinatorial object and eliminates intruders. This can be done for independent families. And in fact, what we realized is that one can add an arbitrary large number of reals, as many as we wish, which simultaneously extend a given independent family are mutually independent. So this allows us to generate a very large independent family. But in order to provide maximality, we have to diagonalize. So just the product of such mutually diagonalizing reals will act as almost like conreals. We'll be able to generate an independent family of size Aleph omega, but where do we get maximality? Well, we have to, in fact, diagonalize the minimum number of steps we need to diagonalize with these techniques, which is omega 1. All right, so so the poset which would allow us to generate a maximal independent family of desired size is just a large product of diagonalizing real, an iteration of large products, and this is just a short iteration. All right, so these ideas essentially allow us to provide two things. The spectrum can be arbitrarily large, but also this partial order is very nice. It is almost like Heckler forcing for adding a MAD family of desired size, almost. That's maybe a big simplification, but we can do an isomorphism of names argument. And this isomorphism of names argument allows us to have a precise evaluation of the spectrum. So not only we can guarantee that there are arbitrarily large witnesses, but we can exclude everybody else, which is usually the more difficult task. All right. Okay, so we can control the spectrum, but we are very far from providing witnesses, good projective witnesses for these members of the spectrum. Okay, so going back to independence, there is a number of results which show that selective independent forcings are indestructible by various partial orders leading to various constellations. You can see this is the original result of Schellach. Then we could show Miller partition forcing, coding with perfect trees, H perfect tree forcing, Miller light forcing, and there are also interesting results related to free sequences. David Fudonsky is in the audience. Jan Grabik also worked on this. So very nice. So every time we literally sat down, developed some very interesting combinatorial forcings. For example, in the work with David, we looked at equivalent with party forcing, which we started. I think it's still open if it is equivalent to Schellach's original forcing. So some very interesting combinatorial facts. All right, so where I'm heading to, there is a general framework which actually shows all of these results. What it turns out, the properties which are responsible for this indestructibility are very simple. All that we want from our partial order are the following two things: that it is Kohn-preserving, this is the definition, and and that it preserves dense maximality, which is much simpler to check than to check that it actually preserves selectivity, which speaks about this density filter associated with the independent family. All right, so let me check the time. So so we have tight, maximal, eventually different families, which were very robust. We got them with a lot of work. Now we have these selective independent families, which probably can be read from the paper 1984, but it took us a lot of time to realize what really we want from our partial orders. We just want very little, this Kohn preservation and preservation of dense maximality. All right, and now another interesting combinatorial object, the last one that I want to comment on is, all right, this ideal independent families. All right, so ideal independent families can, in a certain sense, be viewed as a generalization of both almost disjoint families and independent families. So what is an ideal independent family? This is a family of infinite subsets of omega, which has the property that no member of the family is covered by finitely many other members of the family. So for every set A and every element of the family and then any finitely many other family, A is not almost contained to this union. So this is an ideal independent family. Again, an ideal independent family is maximal if it is maximal under inclusion. And the least cardinality of such independent family is denoted SMM. I have no idea how from ideal independent we go to SMM, but there is a reason most probably. And so both almost disjoint families and independent families are both examples of ideal independent families. All right, so in fact that's a very recent paper of Arnie Miller, Jonathan Cancino, and Osvaldo Guzman, in which they studied these ideal independent families. I think the paper is from 2021. And they show that it is always above D and the Ripping number, the dominating the Ripping number, and that they show that each of the following inequalities is consistent. So in particular, they show for this inequality that there is an ideal independent family which survives a large product of sex forcing. All right. And for this, they use diamond, and it's very interesting and beautiful construction. But after looking at all these previous examples, once we looked at the proof, so seriously, products but no iterations, what is going on? All right, so we started looking at these questions, and it turns out some associated filters are to a great extent responsible for these indestructibility properties of ideal independent families. And these filters are naturally associated to the family. So if we have an ideal independent family, we look at the collection of all the complements, all right, the trace for any set A, we can look at A minus finite unions from the family. We know that this is a filter by definition, and we refer to these filters as complemented filters associated to the family. And these complemented filters will turn out to be very useful for us. So, so what is interesting is that an ideal independent family is maximal if it gives us such a nice covering of the power set of omega. Now, on one side, we have the ideal generated by the ideal independent family, and on the other hand, we have the union of all complemented filters. Now, for people who know what dense maximality is for an independent family, it's interesting to mention that we have that an independent family, not ideal independent family, is densely maximal if and only if we have a similar partition of the, it's a partition in this case, of the power set of omega, some covering of the power set of omega associated through the density filter of the independent family. Okay, so that's maybe a bit. There is some interesting analogy. All right. So, first surprising result, looking at this structure, we show that, in fact, this SMM is greater or equal than the ultrafilter number. And that was for us surprising. And as a consequence, we obtain that the number SMM and I are, in fact, independent. And that's somehow unexpected. We've been looking at this combinatorial cardinal characteristics for a long time, and yet there are new results which are still appearing. And all right. All right, so one can start asking, what is the structure of these complemented filters that allows us to obtain indestructibility? And I'm going to hurry up a little bit. So this one can require a lot of properties on these filters. For example, we can show that if the pseudo-intersection number is the continuum, then there is a maximal ideal independent family with the property that all complemented filters are PC points, and we can control those even more clearly. And here comes the object that I want to show. Suppose we have an ultrafilter. We say that the maximal ideal independent family is U encompassing. If the following conditions hold, it lives in the dual ideal of this ultrafilter. And moreover, for every member of the ultrafilter, the set of elements of the ideal independent family, so that X is in the associated complemented filter, is everything but countable. It is co-countable. All right, so what it will turn out, it's almost the end of my talk, is that this E encompassing ideal independent families are very robust under various forcing constructions. They can survive various forcing extensions and are indestructible. So here we have, first of all, under CH, if we have a p-point, then there is such an object. There is an U encompassing maximal ideal independent family, such that all associated filters are a p-point. And here is this main result. Suppose that we have a p-point, a forcing notion which is proper omega-omega bounding, which preserves p-points. Then this forcing notion preserves the maximality of any U encompassing maximal ideal independent family, which has the property that these complemented filters are p-points. Aha! So in particular, we show that under CH there is an ideal independent family which survives, whose maximality survives any extension obtained by a proper omega-omega bounding p-point preserving forcing notion. And so we obtain various constellations associated to this, yet another interesting combinatorial objects to which we stumbled just looking at various constellations and witnesses for this SMM. All right. So there are some interesting open questions associated to SMM. In particular, it is open if the minimal cardinality of this maximal idea independent family is smaller than the almost disjointness number. Otherwise, the work that we have so far, together with the work of Cancino, Guzman, and Miller, essentially determines the relation between SMM and any other of the classical cardinal characteristics. So this is the open question which is associated to this combinatorial object. All right, so there are various interesting questions. All right, so that's about preservation and small witnesses. Okay, can we have arbitrary size? Remember, preservation gave us always size aleph 1. Is there a diagonalization property for such ideal independent families? Well, after some work, yes, there is. We can generate ideal independent families in an iterations by just adding one new member to the family. We have this diagonalization property similar to what we have seen for eventually different families and independent families. And this allows us to control the spectrum of such ideal independent families, maximal ideal independent families. What we know about the projective complexity, this is working. We know currently almost nothing. It's all to be done, but it seems that there is a lot that one can at least try to say. What is still left? Similar to the independence number, we do not know if this minimal cardinality, we can force an ideal maximal ideal independent family of cardinality alpha omega. We do not know, and the available techniques do not seem to give us the answer if consistently SMM can be alpha omega. And there are a number of open questions regarding what are the possible sizes, what is the spectrum of SMM. We don't know if it is closed with respect to singular limits, and there are other obvious questions that one can ask which are still open. So it is very new, it seems, even though it is a classical object, it seems that it somehow it's not that well understood. All right, so where we are, I have minus few minutes. So this is some of the most popular combinatorial cardinal characteristics. So SMM is right here above the ultrafilter number. We know about its relation with everybody else except the almost disjointness number. We do not know if they're independent. And we don't know also if the independence number and A are mutually independent. So why am I pointing this out? Well, so for a long time, and even when we were talking about SMM, our first task was to see how does it compare to the other combinatorial objects that we know. And we saw we actually proved something new. I mean, it is interesting, that's very natural. But with the development of our understanding of all these classical characteristics, this list is not exhaustive. I mentioned already a lot of combinatorial objects that do not appear on this scheme. The game changes. Now we are interested in more sophisticated constellations. If I have 2 or 3 characteristics, and these are the ZFC dependencies, I can wish to realize a constellation which is not forbidden by these ZFC relations. And it turns out that this is extremely difficult. So on the other hand, this seems to be the natural questions that we are looking at. All right, that's all. Thank you.
Thank you very much, Vera. Thank you.
Well, under a lot of large cardinals, this thing don't exist. Okay, so can you please repeat your question? Yeah. Yes.
There's going to be an extended coffee break now, and there's a poster session.